Hi everyone, myself Pranjal Saxena. I am currently a second year PhD student at IIT Kanpur in Aerospace Engineering Department. So in this video, it's a continuation of a 3 video series where I've taught how to make meshes in Abaqus in 2D and 3D, giving some simple examples. And then I have written a code about how to import those meshes from Abaqus to MATLAB. In the second video, I've explained that. Now I want to explain the issue that I have faced while using Abaqus for higher order meshing. Let's say for quadratic meshes, we have these internal mid nodes, which I have found are not same within tolerances. Let's say if I want to have a mesh accuracy of certain order, the mid nodes are off by some value. So in this video, I'll try to explain the issue and the steps I have taken to somehow mitigate those issues while writing that code. So let's get started. First of all, we'll just go to the basics. We'll create 2D shape functions for second order. So what happens actually in a 2D environment, it's a product of two lines. So let's say for node 1, we want to have the shape function of value 1 at this node and 0 everywhere else. So what we'll do, we'll pass a line from node 4 and 6 and then a line from 3, 5 and 2. Then multiply those two lines and then normalize the coefficient. So this xi plus eta minus half is the line connecting 6 and 4 and xi plus eta minus 1 is the line connecting 3, 5 and 2. Putting the values xi and eta as 0, 0 of this node 1, then what we'll get the value as 1 by 2. So to normalize it, we multiply it by 2. So this shape function, this is the first shape function corresponding to node 1. This will attain a value 1 at node 1 and 0 everywhere else. Similarly, we'll create shape functions for node 2, 3, 4, 5 and 6. So these are the corresponding shape functions with the normalized coefficient. Then we'll expand these things. So this is the expression that you'll be getting. Now let's take a 2D triangle, a physical triangle. This is not in the master space, this is in the physical space, xy coordinates. So in isoparametric concept, what happens, we map these physical coordinates to the master coordinates using the nodal values. We have associated nodal shape functions, we just multiply it by the value of the coefficients at these nodes. So let the coordinates be A, B, C, D, E and F, where D, E and F are the corresponding midpoints of the edges as shown in this figure here. Now we go to the mapping. Mapping is just xi ni hat. So we just take the transpose of the coordinates multiplied by the shape functions. Now we convert this problem into a vector containing a combination of the coefficients multiplied by these values xi square, eta square, xi, eta and 1. So what happens whenever we are dealing with a linear geometry, let's say straight edged physical triangle, no matter what the shape of the physical triangle is, the mapping from the physical triangle to the master triangle has to remain affine. What this means, affine means linear with a constant. If we replace D, E and F as the corresponding midpoints, the first three values of this vector vanishes. So we'll be having no coefficients multiplying to xi squared, eta squared and xi eta. So this essentially says that whatever be the order of approximation used, if a straight edge triangle is mapped to a straight edge triangle, there is no need for higher parts. So the mapping remains affine and the approximation properties of the element, the physical element, are ideal. Ideal in the sense that they are complete up to that certain order. In this case, the shape functions in the physical element also will be complete up to quadratics. But whenever we are dealing with Abaqus meshes, this is an example that I've used in the previous video. This was the mesh file that I've created using Abaqus. So it has a two element system. So now these nodes 9, 6 and 7 has to be in the middle of 9 has to be in the middle of 1 and 4, 6 has to be in the middle of 1 and 3, 7 has to be middle in 1 and 2. But for this element 1, the node 6, this E node, as per Abaqus, the corresponding coordinates of node E is 7.07106781. While if we take the midpoint of B and C, that is node 1 and 3, the midpoint comes out to be 7.0710678. If you will see that the difference is in the order of 1 e to the power minus 8. So this doesn't seem much, but I'll show you with an example that this actually deteriorates the mapping from being an affine mapping to a higher order mapping, and eventually it will reduce the approximation properties of the element. The final convergence rates or the final errors will be worse than the optimal rate. Let me just quickly go to a MATLAB program that I have written. So this is the MATLAB program. Here what I have done, I have just written the shape functions and the derivatives. There was no need of derivative though. Then I have created nodes. For the node 1, I am having a 6-noded triangle having the same coordinates as the master triangle. So the mapping reduces to x equals to xi and y equals to eta. But what I'll further do in second category, what I'll do instead of this, the node 4, this one, instead of 0, I'll write 1 e to the power minus 8, so that the value is off by an order of 1 e to the power minus 8. In the next set, what I'll do, I'll further enhance this to incorporate one more change. This, instead of 0, again I am writing 1 e to the power minus 8. So I'll just quickly run this program. So what you'll notice here, the map 1 is x equals to xi and y equals to eta. But when we are going to map 2, x is xi, that is good, but y is now a function of eta, xi and a combination of both. So it is having higher order terms in zeta, eta and zeta square. This is actually a very deteriorating effect on the approximation property of the element. So even if we are just off by a value of 1 e to the power minus 8, we still have to face the consequences of lower approximation properties. Similarly, for the third, when we are having both values off by 1 e to the power minus 8, we are having quadratic mapping for both x and y. So with this example, I want to reiterate the fact that the Abaqus meshes needs a further enhancement so that the values are not off even by small values. Let's say for the order of 1 e to the power minus 8, so that the results that we are getting using these meshes are more accurate. So I hope I am able to communicate this idea with you about the issue that I have faced using Abaqus. Please comment down below if you have faced similar issues or some other issues. I'll try to help as much as I can. Thank you for your time.